All right, we are back online and streaming. Welcome to everybody out there on the live stream and watching in Twitch. And if you're logged into Twitch, you can comment. Just drop comments and questions in the margin there in the stream chat in your Twitch window. If you're watching this and you're not logged into Twitch, you can also jump into our Slack channel, in the doctor's office channel. Ask questions, get me to clarify stuff. Really, this time that we spend together in virtual office hours is meant to help you as much as possible. So this is a great opportunity, as I'm going to work through some problems here, for you to ask me questions, and we can engage in a conversation live here while we're working through some problems. So it's week 2 of our Math 105 online course, Mathematical Thought and Practice. And this week we're kind of taking what we did in the first week, which was learn some basic ideas about sets and subsets. And trying to extend that, broaden it out a little bit more, make it a little bit more valuable, a little bit more useful, give us some more good problem-solving strategies and approaches. And what that ends up looking like this week is we start to get into some problems that involve Venn diagrams with 3 sets in them. So Venn diagrams with 3 sets. And one of the big things that starts to happen when we work with Venn diagrams with 3 sets is that we also, in particular, really pull in a lot more information about set operations. Mathematicians call this actually the algebra of working with sets. It's a way of taking 2 sets, for example, and producing a third. Just like with arithmetic of numbers, when you add numbers, you're taking 2 numbers, and by adding them together you make a third. Well, it's the same thing with sets. You take 2 sets, you apply an operation, union or intersection, for example, to them, and then that produces for you a third set. So I do want to spend some time, especially devoted to set operations in today's live stream, because not only is it a valuable tool, it's also something that I noticed a lot of people having some difficulty with when you're working through the me time assignments. So I do want to make sure that we get a good opportunity to dig into set operations today. So that's one avenue that I want to make sure that we get a chance to talk about. The other, sorry, I'm just rearranging my windows here so I make sure I can see the chat. There we go. The other avenue that I want to make sure that we go down together today is to really start looking at some of these application problems, and in particular, the applications that reside in this portion of the course are applications to surveys, which really is an opportunity for us to use this Venn diagram structure that we're learning about to really get and do some looking at data, the way that we see data and the way the data shows up in real-world context. So survey problems are a way to get us to use Venn diagrams to think more critically about how surveys work and what they do. So let's just dig in. And kind of what I want to do is I want to start from the bottom and work our way up. So let's start with a survey problem. And then along the way of really taking the survey problem apart, we'll take the opportunity to bring in set operations and bring in Venn diagrams with 3 sets. So let me pull out a survey problem here that we can start to work on. So let's start with just a survey problem that's a little bit on the simpler side. So the survey problem we're going to start with is not going to involve 3 sets, but it's really only going to involve 2 sets. So we'll start there, and then as we get a little bit more sophisticated as we go through today's live stream, we'll have the occasion to do some more complex ones. So here comes a survey problem. So suppose that we took a survey of 1,000 adults. And in that survey of 1,000 adults, we asked them what kinds of investments do you have? Are you invested in stocks? Are you invested in bonds? Are you possibly invested in both? Or might you be invested in neither? So we're surveying them about their investments. Where are you holding your money? And so here are the results of that survey. The results of the survey was that 650 of the respondents had investments in stocks. 550 had investments in bonds. And in the survey, 400 respondents were invested in both stocks and bonds. And so we get some information in this survey about people's investments and so forth. And the kinds of questions that we might ask then, based on what we have in this survey, are things like, all right, given this information, I'd like to know something like, how many are invested in only stocks? And another kind of question that we might ask here is, how many invested in neither? So how many people in this survey, how many respondents, are neither invested in stocks nor invested in bonds? So we have enough information, it turns out, just based on what we're seeing here, to be able to answer both of those questions. But the trick, really what makes survey problems interesting, is the way in which people in a survey are really only giving one response, but then they may be being counted in more than one location in our final data. So for example, if I were one of the respondents in this survey that was invested in both stocks and bonds, so I'm part of this 400, that means that I'm part of this 400 number, but that also means that I'm part of this 650 number because I'm invested in stocks, and I'm also part of this 550 number because I'm invested in bonds. So if I'm one of these people, I'm getting counted in 3 different places in this list. And the trick is, we want to try and take apart this information in a way in which each respondent is only counted once. Right? And the best way of doing that is by using a Venn diagram as a tool to make this all happen. So let's get started on bringing a Venn diagram strategy to bear on a problem like this. So first we'll look through the categories that we're trying to sort respondents into in this problem. So we're trying to sort respondents into those that were invested in stocks and those that were invested in bonds. So that suggests to me that what I ought to do, or one valuable strategy, might be to take stocks and bonds and make those two things my two sets. So I'm going to write that down here. So let's let A be the set of respondents who were invested in stocks and then I'll also write B is the set of respondents invested in bonds. And by the way, I'm using generic names for these sets. I'm calling them A and B, but there's really no reason that I should be generic with my set names if I'm making up the sets. If my sets have a context, right, if I want to make it easier for myself later to understand what these sets mean when I'm using notation to do things like perform operations on sets, then I might as well take the liberty, because these are my sets. I own these, and when you do problems like these, you own those sets, right? Don't let the textbook dictate notation for what letter that you use to represent your sets. The same is true for variables later on, right? When variables represent real things, then it's really handy to use meaningful names to name them. That way it makes it easier on your brain to understand what you're doing with those variables later on. So instead of using A and B, let me use S and B. So S is the set of respondents that are invested in stocks. B is the set of respondents invested in bonds. And so what we want to do then is make a Venn diagram with those two sets. So I'll put in one circle here for my set S of respondents that are invested in stocks. Sort of make my letter S here to remind myself that that's what this is. And then likewise for B. So here's my set of respondents who are invested in bonds. And then there's one other thing that I want to put in this Venn diagram. there's not always something that we think about explicitly, but it probably should be, and that is the universe, right? So we have to define sort of who all is a part of this whole Venn diagram. If you're not part of S or you're not part of B, then what are you a part of? We call that U our universal set. And I'll take the occasion here to, well, this is a capital U. I'll write down here that U, the universe, is the set of all respondents to this poll, this survey. So, because there's 1,000 elements in this universe, it's not going to be practical for us to do as we've done in previous Venn diagram problems and just literally list every single element, right? It's not practical for us to come up with a roster for any of the sets here, just because they have too many elements in them, right? I don't want to sit here and write out 1,000 elements. So this is a great example of the kinds of problems that mathematicians like to develop strategies for, because it's not practical to be super concrete about the elements, but we would still like to know information about these sets. In particular, when we're asking about survey problems, we're answering questions like how many. And if we're answering questions about how many, that means what we're really asking is, what are the cardinal numbers of various sets that we could ask about? Right? So we want to understand the cardinal numbers without being able to write down a roster and actually put our fingers on the elements of these sets. So how do we count the elements in these sets without explicitly listing them all out? That's what makes these problems interesting, and it's what calls for some strategy in order to make this happen. So I'm going to preface this by saying that when I write down anything in this diagram about these sets, what I'm going to be writing down are not the elements but the cardinal numbers of these sets. For example, the cardinal number of U, the universe, U is the set of all respondents in this survey, that cardinal number would be 1,000. Right? So the problem, though, is that if I write 1,000 in here, then because I just wrote that outside of S and B, this makes it look as though all 1,000 respondents are not elements of S or elements of B. In other words, neither invested in stocks nor in bonds. And that's not true, according to our data. So I don't want to write any cardinal numbers in here just yet, until I've figured out exactly how to use the information that's been given to me. Now, let's think about how we can use that information as strategically as possible. I'm going to clear out a little bit of space here so that we can write some stuff. So how do I use this information? Well, 650, since we defined S to be the number of people invested in stocks, that 650, all 650 of those people must be inside of this yellow circle. This circle in my Venn diagram, the region in my Venn diagram where the stock invested people reside. Similarly, this 550 people have to be inside of the red circle. The problem is that those two circles are overlapping one another. And so some of the people in the yellow circle they also need to be people in the red circle. Fortunately for us, we explicitly know how many elements are in that overlap of two sets. There's 400 people in this problem that are invested in both stocks and bonds simultaneously at the same time, right? So here's the key strategy for assessing survey problems. The key strategy is to begin with the information that involves the most overlapped sets. So work your way out. Work from the overlaps outward. So in our two-set Venn diagram, we're going to start by looking at the region where my two sets overlap one another. Then we'll work our way one step out and ask, all right, how many elements in the yellow set, S here, don't belong to this overlap? How many elements in the red set don't belong to this overlap? And then our last step will be to work our way all the way out of both of those and figure out how many people are in the universe but are in neither the set B nor the set S. So we're going to work from the overlaps outward. And fortunately, again, for us, we have this great piece of information that there's 400 people who are invested in both stocks and in bonds. And what that tells me is that there's 400 people that belong to the set B and the set S at the same time. So there are 400 elements that are in both B and in S. And so that corresponds to this region here, this overlapped region, which I'm going to color in here, just so that we get a sense of what is representing what. So this region of overlap in between S and B, that's where my 400 people are going to live. And so, as I'm working my survey problem, the first thing I'll do is I'll go into that overlap and write down, because now I know exactly that there's 400 people, 400 respondents to this survey that live in that overlap. Before we go any further, I want to tack this back into set operations. So the set of people, the set of respondents who belong to both of these two sets, is also a set. And it's a set that's related to the set S and to the set B by a set operation. So we call this operation, we talked a little bit about this in our first week live stream, we call this operation the intersection operation. So the set is called the intersection B intersect S. This consists of those elements that belong to both B and to S. So the intersection B intersect S. That's the orange set that I just shaded in this Venn diagram. So there's 400 people in that intersection, 400 respondents. So now we want to work our way out. And the idea here is that now that I know there's 400 people that are in both stocks and bonds, the next question that I'm interested in is how many people are in only stocks. Right? So not stocks and bonds, but only stocks. Stocks and not bonds. Because it's not 650. 650 is the total inside the yellow circle. So let's think about how we would sharpen that question a little bit. If I want to know the number of people that are in stocks but not bonds, or maybe I'll say it this way, stocks and not bonds, well, we have this key word "and" that's showing up here again. And so that indicates that we're also dealing with another intersection, if we want to express this using notation. And it's going to be the intersection this time of S with the set of people who are not invested in bonds. And the set of people in the Venn diagram who are not invested in bonds is everybody outside of the red circle. So everybody outside of the red circle doesn't belong to B, but it belongs to the set of things which are not in B. We call that the complement in set theory. And we use a superscript C to represent that in notation. So to say stocks and not bonds is to say the intersection, so that's where the "and" is showing up in our notation, the intersection of the set of people who are invested in stocks with the set of people who are not, complement, invested in bonds. And that's this yellow shaded region over here. So now that's the set that we need to figure out. Now, we know that there is a total of 650 people that are in the yellow circle. They're invested in stocks. 650 in stocks. And we also know that there's 400 people that are in both stocks and bonds. So if I want to know how many people are only in stocks and not bonds, they're going to make up the difference between these two. Right? So to figure out how many people are in just stocks, what I really need is to subtract 650 minus 400 in only stocks. So what that's doing is it's removing the double counting that's happening, where previously the people who were in both stocks and bonds are counted both here in both stocks and bonds, and also being counted in the 650 number. So subtracting them away ensures that the 250 that remain are only being counted once. And as you work through these kinds of problems, every time you do a step like this, it's a good idea to check back and make sure that your diagram is still representing this information over here adequately. So if I know now, if I'm going to write 250 here and 400 there, then if I just squint my eyes and look only at the yellow circle, I can count in my yellow circle, there's a total of 250 plus 400. There's 650 people in my yellow circle. And that turns out to be exactly what the information in the problem was telling us. There's 650 respondents who are invested in stocks. So this is what I mean when I say we're working our way outward. We're starting from the overlaps, we're starting from the intersections in the middle of the Venn diagram, and then marching our way outward, making sure that as we go, each respondent or each element in the regions of this Venn diagram is only being counted once. So now there's 250 people in the yellow circle who are not in the red circle. There's 400 people who are in both circles at the same time. And so now, before we can get all the way to the outside, we need to figure out how many people are in bonds but not stocks. So the opposite question from the one that we just tackled. So let me shade that region. And I'd like to know how many people are in the red region. So of course, we do the same process as we just did. I want to know how many people are in only bonds and not stocks. And in notation, bonds and not stocks. Again, the presence of this "and" should cue us into the fact that we're going to have an intersection of two sets when we're describing this using notation. We want our respondents to be members of the bonds set, so B is going to be one of our intersecting sets. And the other of our intersecting sets will not be the set of stocks, but the set outside of stocks, so the people who are not invested in stocks. So once again, the presence of this "not" indicates that we're going to have a complement. So upper superscript C. And the thing we're taking a complement of this time is the set of stocks. So when I read this, I'm looking for the people who are invested in bonds and not stocks. That's how we can read that notation. So now that we have that, then all we need to do is apply the same procedure to this question that we did to the previous one. So looking at the diagram, I've got 400 people in this intersection, but how many people do I have in the red circle total? Well, that total is the number of people that are invested in bonds. And there's, according to our data, 550 of them. So there's 550 people that are invested in bonds, 400 that are invested in both stocks and bonds. And so if I want to know how many are left over inside of this red circle but not inside of the yellow circle's overlap, I just need to subtract 550 minus 400, and I find out that 150 are in only bonds and not stocks. And now, again, anytime you write a new number in one of your Venn diagrams, it's a good idea to go back and just double check that everything is still lined up the way that you expect it to be. Whoops, sorry. These 400 and these 150 here are all part of the red circle. If I add them together, I get 550 people in the red circle, and that's exactly what I have in my original data. There's 550 respondents who are invested in bonds. So now every region in my Venn diagram has been accounted for but one. The only region we haven't accounted for yet is the white region, outside of B and S, but still inside of my universe. And those would be the respondents to my poll who are not invested in bonds, so they're outside the red circle, but who are also not invested in stocks, outside the yellow circle. These are the people that are invested in neither stocks nor bonds. So the last thing we ought to do to finish our Venn diagram is to figure out how many people are out there, how many respondents, how many elements are in neither the set B nor the set S, but are still part of our universe. So to do that, the first thing I want to know is how many investors are there total? Regardless of whether they're in stocks or bonds, how many people are inside one or both of these two circles? So our last step here is going to be how many are invested in either. stocks or bonds. And this too is a kind of set operation. It's one of the ones that we also talked about in our first live stream last week. The presence of the keyword or here cues us in to what's called a logical disjunction, or called a union. So this is going to be the union of two sets that we're talking about now. And it's going to be the union, of course, of the set of B, the set B, the set of people invested in bonds, and the set S, the set of people invested in stocks. So that's the set that we're asking about now. How many people are invested in one or both of these products? And since we've now labeled our Venn diagram in a way where the mutually exclusive regions are labeled separately, right? There's no more, this 250 doesn't overlap with this 400, doesn't overlap with this 150. Now that I have all these labels here, and they're all separate, nobody is being double counted here, I can figure out the cardinal number of this union just by adding these three together. So cardinal number of this union is going to be 250 plus 400 plus 150. Add those up. 250 plus 150 is 400, plus 400 is 800. So in our Venn diagram, there's 800 people accounted for inside of these circles. But if there's 800 people inside the circles, that must mean that there's some left over that are outside of both circles. Because after all, my universe has 1,000 people in it. So maybe I can sort of make a little comment here, outside here, that my universe has 1,000 people in it. There's 800 that are inside of this MasterCard logo here. I actually inadvertently made it exactly the MasterCard logo with the colors, so they're not sponsoring me, don't worry, Twitch. But the 200 people that are left over are therefore outside of both of those regions. Why 200? Because it's the 1,000 that make up the universe minus the 800 that are inside one or both of those two circles. So we would call that not the union. The union is the people that are inside both circles. We would say that it's the complement of the union. So if we write that in words, these are the people who are not invested in stocks or bonds. Okay. So it's the complement of the union of S with B. And its cardinal number is the cardinal number for the whole universe, 1,000, minus the cardinal number of S union B, which was 800. So at this point in a survey problem, because we've labeled every single mutually exclusive region in my Venn diagram, and in any Venn diagram with two sets, there's always four regions to label, right? There's the intersection of the two sets, there's the what's called the symmetric difference of the sets, so those elements which belong to one set but not the other, so that's this yellow region and this red region. And then finally, there's the complement of everything, right? There's the region that's in the universe but is outside of both of those two sets. So always four regions to label in a two set Venn diagram, sorry. And now that we've labeled them all, that means that we can now answer any survey question about this data that's thrown at us. So let's go back to the original questions that were being asked. How many respondents were invested in only stocks, and how many respondents were invested in neither stocks nor bonds? And now all we have to do is read that information off of our Venn diagram. How many people were invested in only stocks? Well, that's people in the yellow circle but not the red circle. That's my 250. How many people are invested in neither stocks nor bonds? That's take away everyone inside the circles and only look at the people outside the circles. That's 200. So that's an example of a two-set Venn diagram survey problem. Okay. And it took us a half an hour to work through. That's mainly because I was talking through every step. But what I hope that you take away from this portion of today's live stream is really about the process and the strategy, right? What did we do to make all of this happen? And the big idea of the strategy was the idea of working our way from the inside out, the innermost overlaps, the innermost intersections in the survey, in the Venn diagram, and then work our way out using the information that we have until we've gotten all the way out to the complement of everything, the complement of the union of all of our sets. And at that point, we then have labeled every single possible region in our Venn diagram. The other thing to take away from this along the way was the way that we used notation and set operations to talk about the sets that we were interested in this problem. So we used the intersection symbol to talk about this 400. It was the intersection of S and B. We also used an intersection and a complement to express the notation for this 250 and 150. The only stocks and only bonds group was also an intersection. It was an intersection of S with the complement of B, right? So this is S but not B, and then conversely for this one. And then finally, we ended up using a union and a complement to express the set of everything which didn't belong to either or of these two sets. So those are the two big takeaways from this, is strategy for solving survey problems, working from the innermost intersection towards the outside, eliminating double counting as you go, so there's a lot of subtraction, and double checking. Double checking is the best thing you can do in solving any kind of problem, but particularly multi-step math problems. That if you develop the ability to check your own work as you go and to monitor your own correctness, it's way better if you catch those errors along the way than if you have to wait and I catch them on your quizzes or on your exams, or your employer catches them when you make them at work. You know, it's much better if you have the ability to check your own process. It's called metacognition, being able to think about your own thinking, your own learning, your own process. That's super valuable. So take extra time to do it, and that'll pay off in the long run. And then finally, the uses of notation and the set, union, intersection, and complement operations. So I want to pause for just a minute or two, catch my breath a little bit, and see if there are any questions for people who are watching right now on the live stream. If you have a question about the example that we just did, throw it into Twitch, throw it into our Slack channel. If you have an example of a problem you'd like to see us do next, happy to look at that too. Otherwise, I've got a problem in my back pocket that I can use to continue. But I'm going to just pause for a minute or so and see if there's any questions that arise that people would like to see addressed before we move on, take our next steps. So we'll start again in just a minute or two here. Getting a couple questions coming through in the Slack channel, so thank you. Let's pick up on All right, so we have a question coming through on the live stream for today, and it's a question that will take us back to the quiz from last week. So what I think I'll do is go over that question some, and then try to take it a couple steps further and turn it and ask some additional questions about it that will help us to sort of stay into this week's material also. So let me pull up a copy of the quiz from last week. Just give me a second here. All right, yes, good. So what this question from the quiz from last week asked you to do is it asked you to draw a Venn diagram and then use roster notation to express the union of two sets. So this is great. I mean, it keeps us grounded in what we're talking about this week and gives us an opportunity to refresh how set builder notation works. So here is what that problem looks like. just make sure I can fit it on the screen here. And have it be readable. Sorry, just trying to get this. There we go. So here's what it looks like. It asks you to, first of all, consider these two sets. A is the set of two x's such that x is a natural number and x is less than 6. B is the set of x squareds such that x is a natural number and x is less than or equal to 5. Draw a two-set Venn diagram to represent the elements of those sets. And then, secondly, to use roster notation representing the union of these two sets. So let's tackle this problem, and then what I think I'll do is after we're done talking about this particular problem, I want to add a third set. I'll add in a set C, and then we can take another couple steps forward on top of that. So let's start with just write out the two sets that were given to us here in the problem. And when I scored these quizzes this week, I noticed that a lot of people were having some difficulty reading through the set builder notation for these. But it wasn't, people weren't completely lost, because a lot of people were able to get half of the notation down pat, and then sort of missed out on the other half. So that's kind of the point that I'm going to want to make here about this. So here's the set A in set builder notation, here's the set B, set of x squareds, such that x is less than or equal to 5. So the question is to draw a Venn diagram showing the elements in these two sets. So let me actually start out. I'm going to go back to our previous slide and just grab the template for a two-set Venn diagram, just to grab a copy of it. There we go. Scoot it over here. All right. So I'm just going to set up my little template for my Venn diagram, and I'm going to use A and B this time to represent my two sets, because that's what we were given notation for. So set A, a set B. And so here's the place where people ran into some difficulty. What I usually recommend doing when it's practical, and it certainly wasn't practical in our survey problem that we did a few minutes ago, but when it's practical to list out a roster for all of the elements in a set, that's a good place to start. So to get there, and this is usually a good practice, to get there, let's take set builder notation and turn it into words. So I want to turn this first into a verbal description for the set. And only after I have a verbal description written down am I going to try to get down to a roster for it. So as a verbal description, I'm just going to start by writing A is. That's what I'm seeing here so far, right? A is. And then when I hit the curly brace, we'll translate that as the set of. A is the set of. And then the next thing that we see as we're reading across this set builder notation is 2x. And that actually is the place where people messed up the most on this quiz. The set of all 2 times x. And then people were generally pretty good about reading the rest of the set builder notation. And the rest of the set builder notation will read such that. And then following the such that came these two clauses. X is a natural number. The natural numbers being the numbers that we use to count non-empty sets, non-empty finite sets. So 1, 2, 3, 4, 5, and so forth. The first numbers that we learn when we're learning numbers in the first place. And then also, we wanted our elements to be less than 6. So that was the last bit. And less than 6. So I'm being really brutal about writing all these words out because I really think it helps that when you're reading through mathematical notation, how your inner voice reads that, even if you're not reading it out loud, and maybe reading out loud would actually help to clarify your thinking, but how you hear it when your silent inner voice reads mathematical notation really impacts how you understand what that notation is saying, the meaning that it's carrying. So if you're struggling with the notation, it might feel silly at first, but try just reading it out loud verbally to see if you're really understanding what the notation is saying. So the way that I would read this is A is the set of 2 times x's, such that x is our natural number and x is less than 6. So let's go a step further here and start by taking the right-hand side of this set builder notation that tells us the criteria for what x's we're talking about in our set, and unpack that. This was a step that most of you did very well on this, right? So what are the natural numbers that are less than 6? They are 1, 2, 3, 4, and 5. So if we're being more explicit about this, we'll say x is 1, 2, 3, 4, or 5. But the part that people didn't do as hot on was realizing that those 1, 2, 3, 4, and 5 are not in fact the elements of this set. They're just the values of x, which determine the elements of my set. The elements themselves are 2 times those x's. And so the elements of my set are not 1, 2, 3, 4, 5, but 2 times 1, 2 times 2, 2 times 3, 2 times 4, and 2 times 5. So most people that screwed this question up on the quiz, that's the reason. That they got the 1, 2, 3, 4, and 5 out of the second half of this notation, but they didn't realize what was happening in the first half. Right? And for that same reason, when we look at the set B, if I read this out, I'm not going to multicolor it this time, but if I read this notation, I'll read it as B is the set of x squareds such that x is less than or equal to 5. And the x less than or equal to 5 part, again, people generally got pretty good. It was the x squared piece that people missed, if you missed it. So B is x squared, where x is, again, the natural numbers that are less than or equal to 5 turn out to also be 1, 2, 3, 4, and 5. Right? But B is not made up of those numbers, it's made up of the squares of those numbers. Right? So the 1, 2, 3, 4, and 5 are my x's, but the elements of my set are the squares of those x's. So 1, 4, 9, 16, 25. 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. Now I have rosters for both of my sets. And generally, not generally, I think universally, if you got rosters for these two sets in this quiz, you did the rest of this problem correctly. It was getting to the rosters, it was unpacking the set builder notation. That is exactly where people struggled the most. So now that we have rosters, let's make our Venn diagram. So the way that I usually like to do this is just by taking my elements of A, 2, 4, 6, 8, 10, and I'm just going to slap them inside of the yellow circle without worrying about whether they belong to red or not. And then same thing with the red circle, 1, 4, 9, 16, 25. So now I have all of my elements are in my Venn diagram, but keep in mind the general principle that in a Venn diagram, no element should be listed in more than one region. So I just have to scan through here and see if there are any elements that are in 2 places. And there's only one element that is in 2 places. It's the number 4. So the number 4 belongs to the set A, the number 4 belongs to the set B, and I don't want to list it in more than one region. So the way that my Venn diagram conveys that information is that it puts that element here in the intersection. Right? Now all of my elements are listed in exactly one place, and I don't have any repetition, and all the elements in my 2 sets, A and B, are somewhere in my Venn diagram. So now my Venn diagram is good. We're all set. But the question didn't end there. There was a part B, as there often is. And part B asked us to find a roster for the union A union B. So let's find a roster for the union. So the question is, what is the union? Again, hearkening back to our set operations discussion from a few minutes ago. Union is our either-or operator for sets. I've kind of put this in quotes here. We're looking for a roster for the set of all elements that are either an element of A or an element of B. So if I wanted to visualize where this is in my diagram, it's going to be everything that's in one or both of my two sets. And so if I want a roster for the union, since I have a Venn diagram already, that's going to be as straightforward as just listing all the elements that I just shaded. So 1, 2, 4, 6, 8, 9, 10, 16, 25. Again, taking care not to list any element more than once. And the reason not to list any element more than once is it doesn't make the set incorrect, right? It just makes it less useful if I ask you what the cardinal number is for this set. And I did ask you that in this question also. So if you happen to list 4 twice, okay, you'll get the wrong cardinal number if you then just go in and count the elements. But now that every element is listed only once, we can determine the cardinal number just by counting up the roster. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's the cardinal number of the union A union B. So does that help to clarify some of what was going on in this question on the quiz? Because again, I want to take this a step further, but before I do, is there any lingering questions or things you'd like to hear more about that related to this quiz problem? Oops. So if not, then I'm going to take this, I'm going to kick it up a notch. Let's suppose that we take these same two sets, and then we also add in a third. So let's wrap this example up by throwing in a third set. And just to get us some more practice with set builder notation, I also want to use set builder notation to express this one. So let's do the set of 2x minus 3's, where x is a natural number, and let's say 2 is less than or equal to x is less than 5. So here's kind of a messy set, especially a messy set builder notation to understand. So before we do anything, let's come up with a roster for C. And before I do that, let me write down my rosters that we had for A and B, just so that we don't lose that information. A was 2, 4, 6, 8, and 10. B was 1, 4, 9, 16, and 25. Now let's come up with a roster for C. Actually, I'm going to change this definition a little bit so that I make sure the problem is still interesting. Let's say 2 is less than or equal to x is less than 9. Okay. So when I unpack this set builder notation, I'm going to read it as the set of all 2x minus 3's so that x is a natural number and x is between 2 and 9. So it's greater than or equal to 2, and it's less than 9. So I'm going to skip a step that we used here before and just list out a roster that describes the x's that are defining my set. The natural numbers that are between 2 and 9, including 2, but not including 9, are 2, 3, 4, 5, 6, 7, and 8. So that, again, this part of my set building notation tells me about the x's, and then the thing to the other side of the line tells me what to do with those x's to determine the elements in my set. So all I have to do is multiply each of these by 2 and then subtract 3. So 2 times 2 minus 1, sorry, 2 times 2 minus 3, that's 4 minus 3, that's 1. 2 times 3 minus 3, that's 6 minus 3, that's 3. 2 times 4 minus 3 is 8 minus 3 is 5, etc., etc., etc. Whoops. So there then is my roster for the set C. Let me move this off to the side so we have plenty of room for our Venn diagram. So now we have rosters for A, B, and C. Let's draw out our Venn diagram with 3 sets. So I'll start out by putting in my universe. Try and make it a nice big square this time. We didn't really say what the universe was for this problem. It's not a survey problem, so maybe we'll worry about that a little bit later if it becomes important. And then inside of that universe, I will put in my 3-set Venn diagram, A, B, and C. And then to make my Venn diagram, I'm just going to do what we did in the last example and take all of the elements that we listed out in our rosters, throw them into the Venn diagram, and then worry about reducing double counting. So worry about making sure that each element appears in only one region. So starting with the elements of A, 2, 4, 6, 8, and 10. Draw those in here, 2, 4, 6, 8, and 10. Then I'll put in the elements of B, 1, 4, 9, 16, and 25. And then I'll put in the elements of C, 1, 3, 5, 7, 9, 11, and 13. Okay, so now I've gotten everybody into the pool at this point. We now just have to reduce our double counting. We have to eliminate the possibility of something appearing in more than one place. So we'll just kind of take the elements one at a time. Let's start with 1. Well, 1 is showing up in 2 places right now. It's showing up in B and it's showing up in C. That means that we need to move it to the intersection of B with C. So 1 belongs at least there. Okay, so we'll put 1 there for now. How about 2? 2 is okay. 2 is only showing up in one place. Likewise, 3 is only showing up in one place. 4 is showing up in 2 places again. It's in A and it's in B, which means that we need to move it so that it belongs to the intersection, A intersection B. So 4 will go there. 5 is only in one place. 6 is only in one place. 7 is only in one place. 8 is only in one place. 9 is in 2 places again. So just like 1, we'll have to move it to the intersection of B with C. 10 is only in one place, 11 is in one place, 13 is in one place, 16 is in one place, 25 is in one place. So now we're good. Now our Venn diagram has all of our elements, and every one of them belongs to only one region of this 3-set Venn diagram. Now we need to use this Venn diagram to answer some more questions about this situation, and I want to get back into using notation for set operations once again. So let's suppose that I wanted to know what is the cardinal number of A union B union C. So remember, union means either or. So what I'm asking is how many elements are in either A or B or C. Right. And so using our Venn diagram, what we would do, what I would recommend we do, is highlight, shade, all the regions that belong to that union. And in this example, those regions would include absolutely everything we see inside of these circles. So to answer this question, I would just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, well, let's get a couple more examples in here. Suppose I want to know what is a roster for A union B, parentheses, intersect with C. So now we're ratcheting up the notation a little bit. So what I have here is an intersection, first and foremost. It's an intersection of two sets. It's an intersection of the set C, so let me shade C for a minute. So it's an intersection of this set with the set A union B. And the set A union B, again, thinking about how unions work, A union B is everything which is in A and also include everything which is in B. So what I'm looking for here is where the orange set and the green set overlap one another. And so if I'm going to shade this intersection, then what I'm going to shade is everything that I've colored both green and orange. So if I want a roster for this set, I want a roster for the region that I just shaded. And so that's only going to include the elements 1 and 9. So having a Venn diagram is like the Rosetta Stone of performing set operations. Because once you figure out how to shade the regions that matter, the regions that you're really interested in, then you can just read your answers right off of the regions that you shaded. Let's do one more. Let's suppose I wanted to know the cardinal number of A intersect B complement union C. So I've got a bunch of stuff going on in this one. So let's highlight some of the sets that we need to shade in order to make this thing happen. First one is the set C. So once again, I'm going to take and just sort of shade in temporarily that circle for C. I also need to shade in the intersection of A with B complement. So let's talk about that one next. So A is everything in this circle here. B complement, meanwhile, remember complement means not. So B complement is everything that's not in B. So I'm going to kind of shade the outside of B, if you like. And draw a little sunshiny rays here to indicate that I'm shading everything outside of B. So if I'm doing the intersection A intersect the complement of B, I want everything that's in the orange circle and is also in the purple shaded region. So A intersect the complement of B is going to be this. This is what we called a symmetric difference before. This is everything that belongs to A but does not belong to B. So what am I trying to count in this problem? I'm trying to count the union of the purple set with the green set. And so that union is going to be what we get when we glue those two sets together. Let me shade that again because you kind of can't see when I colored too heavy. There we go. So here are the regions that matter for this set. And the question's asking for the cardinal number, so all I need to do is count them. Count the elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So getting a feel for how set operations work is really a process. And the hardest parts of the process, I think, that take the most practice are, first of all, decoding set builder notation. That's this thing that's kind of still with us from the first week of the semester, but the more practice that you get with it, and the more that you really take it slow and list out rosters, the better things go. And then the second thing is using notation for unions and intersections and complements, so understanding how those things work. Before we wrap up the stream, there's one more question that just popped in that I want to make sure we have a chance to address. And the question is, will the complement of A union B always have elements of C? So in this example, so let's roll the tape back a few seconds here. The complement of A union B is going to be, well, yeah, let's roll this back, and I can actually write down what this question was asking. The complement of A union B. In other words, A union B parentheses complement, like this. So if I want to shade that set, well, first of all, A union B is everything inside of these two circles up here at the top. So A union B complement is everything outside of those two circles at the top. So A union B complement is going to be all of this. And the question in the stream is, will that complement always include elements of C? And the answer is, well, in this case it certainly does. But you could imagine a Venn diagram in which it doesn't. So maybe C happens to be a set, all of whose elements are shared with one or both of A and B. So in a different world, where maybe my Venn diagram looks like this, in this example, the complement of A union B does not in fact include elements of C. But sometimes it does, like in the first example. Or like if I listed one and two spots, sorry. I don't know, maybe I'll do something like that. So in this example, now it includes elements of C, but if that element's not there, then it doesn't. So there's not a hard and fast rule, and that's why coming up with a Venn diagram in which either every element is being shown exactly once, or, like we did in the survey problem example, every cardinal number of every region is labeled separately. Having that Venn diagram at your fingertips then lets you answer any question that one could ask about any of the regions, as long as you're able to unpack the notation and how the unions and intersections and complements work to tell you which regions to shade. That Venn diagram is your key to everything. So that'll wrap up our live stream for this week. You've got the assignments inside of the online homework on Venn diagrams of 3 sets and survey problems to wrap up. Quiz number 2 is available to submit by the end of the day on Saturday. Also, if you didn't receive credit on quiz 1, you can revise and submit a revision for quiz 1. That's also due on Saturday night as well. So I look forward to chatting about anything math related with you in our Slack channels between now and the next time we get a chance to talk. We'll do another one of these live streams next week where the topic is going to move off of sets, and we're going to start talking a little bit more about logical propositions and logical reasoning next week. So let's all look forward to that, and I hope that you enjoy the rest of your week and your weekend.